Chapter 12, Sound. Sound, a form of energy.
We hear many different types of sounds, ranging from thumping of drums to a note emitted by a flute. When a drum membrane is thumped, it starts vibrating and a sound is produced. The sound reaches our ear and produces a sensation of hearing. Hence, we can define sound as a form of energy which produces a sensation of hearing. In this chapter, we are going to learn how the sound is produced, how it's propagated, and how it produces a sensation of hearing.
Production of sound. Let us try some activities to understand how sound is produced. Activity. Take a tuning fork. Hold its stem and strike the prongs of tuning fork against a hard rubber pad. Now, place the vibrating tuning fork near your ear. You will hear a vibratory sound produced by the prongs of tuning fork. Now, take a pith ball and suspend it by a thread from a rigid support. Strike the tuning fork against a rubber pad and gently touch its prongs to the suspended ball. What do you observe? You observe that the ball is pushed away by the prongs of tuning fork. Why does this happen? Well, this happens because the prongs of tuning fork move to and fro rapidly, due to which sound is produced. This rapid to and fro motion of an object is called as vibrations. This activity shows that the prongs of a sound producing tuning fork start vibrating when struck to a rubber pad. Let us perform another activity with the help of tuning fork. Take a beaker and fill it with water up to the brim. Strike the prongs of tuning fork on a rubber pad. Now, gently touch the surface of water with the prongs of tuning fork. You observe that the prongs splash water. This activity confirms that the prongs of tuning fork vibrates when struck to a rubber pad, producing sound. Now, without striking, gently dip the prongs of tuning fork in water. Do you hear any sound or water splashing? No, it is because the prongs of tuning fork were not struck, due to which the prongs did not vibrate, and hence did not produce sound. We can therefore conclude that sound cannot be produced without a vibrating object. Sound can also be produced by plucking, rubbing, flapping, scratching, or shaking different objects. Here, in each case, sound is produced due to vibrations in the object. Sometimes the vibrations may be strong enough to be seen by eyes, and sometimes so small that can be felt by sense of touch. Flapping of wings by a bird, vibration of strings of a guitar, vibration of a tuning fork when struck on a rubber pad are some examples of vibrations that can be seen through the eyes. Whereas vibration of a mobile phone kept in pocket, vibration of surface of sound box when loud music is played, and vibration of a throat while speaking are the types of vibration that can be felt by touch. Let us now proceed to understand how sound is produced in human beings.
The human beings produce sound with the help of an organ called larynx, which is commonly known as sound box. The larynx contains two ligamentous folds called vocal cords. The vocal cords are stretched across the voice box in such a way that a small passage is created for the air to pass through it. When the lungs force the air to pass through this narrow passage, the vocal cords vibrate, producing sound. There are some sounds produced by musical instruments like flute, violin, veena, etc., which are very pleasant to hear. Musical sound is produced by regular and periodic vibrations. Musical instruments use vibrations of various kinds such as stretched membrane, stretched skin, and air columns to produce musical sound. The musical instruments are thus broadly classified into three categories. They are 1. Stringed instruments, 2. Wind instruments, 3. Percussion instruments.
Propagation of sound.
Let us do an activity to understand the concept of wave. 1. Take a trough full of water and drop a stone in it from some height. What happens when the stone touches the surface of water? At the point of impact of stone with the water, a disturbance is produced. Observe the water surface for some time. You can see waves created at the point of disturbance which move outwards. Now place a small piece of paper on the water surface and drop another stone in water at some distance from the paper. What do you observe? The piece of paper moves up and down, but it does not move with the wave towards the brim. From the activity, we have seen that when a disturbance is produced in a medium, it travels in the medium in the form of waves. Here, the particles of the medium move up or down, and they do not move from one place to other as the wave moves. The medium particles at the point of disturbance vibrating up and down because of the property of the medium make the neighboring particles to follow the up and down motion with certain time lag. This continues and a wave is seen traveling on the surface of the water. Hence, we can say a wave is a disturbance that moves through a medium when particles of the medium set neighboring particles into motion. Thus, wave motion is a mode of transmission of energy through a medium. Now let us understand how the sound propagates through a medium. When tuning fork is set into vibrations by striking it with a rubber pad, the prongs make to and fro movements about their equilibrium position. Let us see in slow motion the movements of the prongs. When the prongs move outward, they push and compress the air layer adjacent to it, creating a region of high pressure or compression. C. As the prongs start moving inwards, they create a region of rarefaction R or low pressure. Due to this, the first layer compresses the layer next to it and undergoes rarefaction. As the prongs move to and fro rapidly in a series of compressions and rarefactions are formed which move in the forward direction. The pressure wave, when reaches our ear, produce a sensation of hearing. Thus, the sound waves propagate through the medium as series of compressions and rarefactions. Sound waves like ripple on the surface of water are called mechanical waves, as they are characterized by the vibration of the medium particles.
Sound needs a medium to travel. Sound needs a medium for propagation and therefore cannot travel through vacuum. Let us perform an activity to demonstrate this. Activity. Take an electric bell and an airtight glass bell jar. The electric bell is suspended inside the glass bell jar. The glass jar is connected to a vacuum pump. Connect the two wires of the bell to an electric battery through a switch. Now, close the switch. Do you hear the sound of the bell? Yes. Now, keep the switch in closed position and start the vacuum pump. What do you notice? Well, you notice that the loudness of bell decreases as the air is taken out from the jar, even though the same current is passing through the circuit. Once the air is fully removed and a vacuum is created inside the jar, you will no longer hear the bell. Let us now understand why does this happen. When the hammer of the bell begins to strike the gong vibrates, due to which sound is produced. These vibrations travel through the air to the wall of the jar. This sets the wall of the jar in vibration, due to which the sound is heard. The sound is heard because of presence of air. But when the vacuum is created inside the jar, vibration could not travel to the wall of jar. Hence, no sound is heard. We can therefore conclude that sound needs a medium to travel. Let us now perform an interesting activity to demonstrate that sound can make a light spot dance. Take a tin can. Make it a hollow cylinder by removing its both ends. Take a balloon and stretch it over one side of the can. Wrap a rubber band around the balloon. Take a small piece of mirror and with the help of glue, stick the mirror to the balloon. Incident light on the mirror fixed on the balloon. You will notice that the light incident on the piece of mirror gets reflected on the wall. Now, shout directly into the other open end of the hollow can.
Hello.
What do you see?
Hello.
Well, you will see the dancing
Hello.
light spot on the wall. Why does this happen?
Hello.
Let us find its reason.
Hello.
When you shout into the open end of can, the sound produced
Hello.
sets the air present inside the can into vibrations. These
Hello.
vibrations in turn cause the balloon to vibrate, due to which the position
Hello.
of light spot keeps on changing. Thus,
Hello.
sound can make a light spot dance.
Sound waves are longitudinal waves. Let us perform an activity to study the direction of vibration to the direction of propagation of waves. Tie one end of a long string to a rigid support such as a wall. Hold the free end of the string in your hand to make it straight. Now, move the free end of the string up and down. What do you observe? You observe that a wave propagates along the strings towards the fixed end. When a wave moves along the strings, particles of the string oscillate up and down about their equilibrium position. Such type of a wave is called as transverse wave. Here the direction of oscillations of the particles of the medium, that is, string here, is perpendicular to the direction of propagation of waves. Let us do one more activity. Have you played with a slinky? Slinky is a very light spring of a long length. Hold one end of the slinky and ask your friend to hold the other end. Now stretch the slinky. Give a sharp push towards your friend. We notice a disturbance traveling along the slinky. Now push and pull your hand alternately. You will observe a series of compressions C and rarefactions R. If you put a dot on the slinky and observe the motion of the dot as the wave travels, you will find the dot oscillates about its equilibrium position in the direction parallel to the direction of the motion of the wave. The waves produced in a slinky are called longitudinal waves. In this type of propagation of waves, the particles of the medium oscillates in the direction parallel to the direction of propagation of waves. Propagation of sound waves through a medium is similar to the motion of disturbance along the slinky. Hence, sound waves are longitudinal waves.
Characteristics of a sound wave.
When sound waves travel through a medium, there is change in density and pressure of the medium. Compressions are regions where particles are crowded together. At compressions, density as well as pressure is high. Rarefactions are regions where particles are spread apart. At rarefaction, density as well as pressure is low. A wave is characterized by its wavelength, time period, frequency, and speed. Wavelength, lambda. The distance between two consecutive compressions or two consecutive rarefactions is called a wavelength. It is represented by Greek letter lambda. SI unit of wavelength is meter m. Frequency nu. As the sound waves move in the medium, density of the medium oscillates between maximum and minimum value. The change of density from maximum to minimum value and again to maximum value makes one oscillation. The number of oscillations per unit time is the frequency of the wave. The number of compressions or rarefactions that cross a point in the medium per unit time also gives the frequency of the wave. It is represented by Greek letter nu. SI unit of frequency is hertz. Time period T. The time taken by two consecutive compressions or rarefactions to cross a fixed point in the medium is called the time period of the sound wave. It is represented by letter T. SI unit of time period is second. S. The relation between the frequency nu and the time period t is nu is equal to 1 upon t or t is equal to 1 upon nu. Pitch. In an orchestra, different instruments produce sounds of different frequencies. All the sound waves travel with the same speed and arrive to the ear at the same time. How does the brain recognize difference in the sounds emitted by a violin and a guitar? This is due to the different characteristics associated with the sound called pitch. For faster vibrations, frequency is higher and hence the pitch is higher. Objects of different sizes and conditions vibrate at different frequencies to produce sounds of a different pitch. When pitch is higher, the sound is shrill, while when pitch is lower, sound is flat. Listen to a song sung by Lata Mangeshkar and that sung by Kishore Kumar. Can you distinguish whose pitch is high? Lata Mangeshkar's voice has high pitch compared to that of Kishore Kumar's. Now let us see how the loudness of a sound is determined. The loudness or softness of sound is determined by its amplitude. Amplitude A. The magnitude of the maximum disturbance in the medium on either side of the mean position is called the amplitude of wave. It is represented by letter A. SI unit of amplitude is meter. The amplitude of a vibrating object depends upon force with which it is made to vibrate. When sound waves emitted by source move away from it, the amplitude and hence the loudness decreases. Timbre. The characteristic of sound, called as quality or timbre, enables us to distinguish one sound from another having the same pitch and loudness. The sound which is more pleasant is said to be of a rich quality. Tone. A sound of single frequency is called tone. Note. The sound produced due to mixture of different frequencies is called a note and is pleasant to listen. Music is of rich quality and hence it is pleasant to listen. Noise is unpleasant to listen. Loudness of sound is different from intensity of sound. Loudness is measure of the response of the ear to the sounds. Intensity of sound is the amount of sound energy passing per second through unit area. Now can you tell me which wave property determines A. loudness and B. pitch? Correct. The loudness depends upon the amplitude of the sound wave and the pitch depends upon the frequency of the sound wave. One more question for you. Can you guess which sound has a higher pitch? Guitar or a car horn? And the answer is guitar has higher pitch than the car horn.
Speed of sound in different media.
Speed of sound V. It is defined as the distance which a point on a wave travels per unit time. Speed is equal to distance upon time. A sound wave travels a distance equal to its wavelength, lambda, in a time equal to the time period t. Therefore, speed is equal to wavelength upon time period. Therefore, V is equal to lambda upon T. V is equal to nu into lambda, because 1 upon T is equal to nu. Therefore, speed is equal to frequency into wavelength. For a given medium under the same physical conditions, for all the frequencies, the speed of sound remains almost the same. The speed of the sound is different for different conditions of the medium. The speed of sound decreases from solid to gaseous medium. The speed of sound increases with increase in temperature of the medium.
Let us now solve numerical examples based on what we have learned. 1.
Calculate distance travelled by a sound wave having frequency of 1000 Hz and wavelength 0.25 meter if it travels for 5 seconds in a certain medium. Solution. Let us first write the quantities given to us. Data given. Frequency nu is equal to 1000 Hz. Wavelength is equal to lambda is equal to 0.25 meter. Time is equal to T is equal to 5 seconds. Distance equal to D equal to what? To find the distance travelled by a wave, we require the speed of the wave and the time of travel. Let us first find the speed of the wave from given data. We have V is equal to nu into lambda. V is equal to 1000 into 0.25. Therefore, V is equal to 250 meter per second. Now the distance travelled by the sound is given by distance is equal to speed into time. Therefore, D is equal to V into T. Therefore, D is equal to 250 into 5. Therefore, distance travelled by the sound wave is equal to D is equal to 1250 meter.
2. A person is listening to a tone of 500 Hz sitting at a distance of 450 meters from the source of the sound. What is the time interval between successive compressions from the source? Solution. Let us first write the quantities given to us. Data given. Frequency
Nu
is equal to 500 Hz. Distance D is equal to 450 meters. To find the time interval between successive compressions, T, the time interval is given by the reciprocal of the frequency of the wave. That is, T is equal to 1 by
nu.
T is equal to 1 divided by 500. T is equal to 0.002 seconds. Thus, the time interval between successive compressions from the source is 0.002 seconds. Reflection of sound.
Sound waves get reflected at the surface of solid, liquid, similar to the reflection of light. Laws of reflection of sound are similar to that of light. Let us do an interesting activity to study the laws of reflection of sound. activity. Make two identical pipes made from cardboards of sufficient length. Arrange them on a table near a wall. Keep a clock near an open end of one of the pipes and try to hear the sound of clock through the other pipe. Adjust the angle between the two pipes in such a way that you can clearly hear the sounds from the clock. Draw lines along the pipes. Also, draw the normal to the wall at the point of meeting of the two lines. Now measure the angle of incidence and reflection. It is found that the angle of incidence is equal to the angle of reflection. What happens if the pipe on the right is lifted vertically to some height? We cannot hear the sound of the clock. The reason is the reflected sound travels in the plane containing the incident sound wave and the normal drawn to the wall. The angle of incidence of sound is equal to angle of reflection of sound. The normal to the reflecting surface at the point of incidence, direction of incident sound, and reflected sound lie in the same plane.
Echo.
If you visit a picnic spot in the mountains, you will generally come across a point called the echo point. When we shout near the echo point, we will hear the same sound again a little later. This sound is called an echo. This is an example of reflection of sound from reflecting surface at a certain distance from the listener. Echo is repetitions of sound due to reflection of original sound from any surface. The sensation of sound persists in our brain for about 0.1 second. That is, our brain cannot distinguish between two sounds if they reach our ear with an interval between them is lesser than 0.1 second. When we shout before the echo point, we hear the sound first. The sound travels towards the obstacle and reflects back to reach our ears after 0.1 second, and we hear our shout once again. This is the echo of our shout. The speed of sound at 22 degrees Celsius is 344 meters per second in air. Hence, the minimum distance the sound should have traveled in 0.1 second is given by distance is equal to speed into time is equal to 344 meter per second into 0.1 second. Therefore, distance is equal to 34.4 meter. This is the distance the sound has travelled from the source, you shouting, to obstacle and back to the observer, you listening. Therefore, for hearing distinct echoes, the minimum distance between the source of sound and obstacle must be 17.2 meter at 22 degrees Celsius. The minimum distance for echo will be different for different temperatures. Due to successive or multiple reflection, echoes may be heard number of times. Example: Gol Gumbaz, a dome in Bijapur, Karnataka. Here, you can hear almost 7 echoes of your voice. The rolling of thunder is due to the successive reflections of sound from the clouds and from the land. Reflection of sound is utilized in measuring the depth of oceans. Sometimes reflections of sound may be undesirable. Which ones are they? These are the unwanted reflections of sounds in an auditorium. An auditorium is designed in such a way that there will be no echo produced harming the sound quality.
Now, let us solve numerical examples based on the concept of echo. 1.
A child shouted hello near a cliff and heard the echo after some time. If the speed of sound is taken as 345 meter per second at a certain temperature and the distance between cliff and the child is 690 meter, calculate the time after which the echo is heard by the child. Solution. Data given. Speed of sound is equal to V is equal to 345 meter per second. Distance of cliff from the child is equal to D is equal to 690 meter. Total distance the sound will travel is equal to distance from child to cliff plus distance from cliff to child is equal to 2D is equal to 1380 meter. Time after which echo is heard by the child is equal to T is equal to what? As speed is equal to distance upon time, therefore time is equal to distance upon speed. T is equal to 1380 upon 345 equal to 4 seconds. Time after which echo is heard by the child is equal to 4 seconds.
Reverberation.
To understand what is reverberation, let us do some activity. Close all doors and windows of the room. Play radio or music system with maximum possible volume. What do you feel? The sound of the music you are listening seems like jumbled and prolonged. A sound created in a big hall gets reflected from the walls and roof and repeatedly reach our ear. The intensity of the reflected sound gradually decreases. The sound reflected by obstacles at different distances reach us at different intervals. This happens till the intensity of the sound gradually decreases and becomes very low to be heard. Therefore, the sound heard seems to be continuous or prolonged. This persistence of sound due to repeated reflection is called reverberation. Some public halls or auditoriums are considered acoustically poor if effects of reverberation are not taken care of. To reduce reverberation, the roof and walls of the auditorium are covered with sound-absorbent materials like compressed fiberboard, rough plaster, or draperies or curtains. The material for the seat is selected such that it is good absorber of sound waves.
Uses of multiple reflection of sound. Some of the applications of reflection of sound are used in the working of devices such as stethoscope, bulb horn, megaphone and soundboard. Stethoscope. This device is used by doctors to examine the patients. It works on the principle of multiple reflections of sound. The stethoscope has 2 earpieces and a chest piece. The doctor puts the earpieces into his ears and the chest piece on part of the patient's body to examine heart and lungs. The multiple reflections of sound waves of the heartbeats or lungs reach the doctor's ears through the stethoscope, allowing him to judge the functioning of the organs. Megaphone. Megaphone or the speaking tube is a cone-shaped or funnel-shaped device used to amplify and direct the voice of a person who speaks into it. It is generally used in small gatherings, fairs, demonstrations and tourist spots. The megaphone has 2 ends. One is a narrow end from where the person speaks, and the other wide end. When the person speaks, the sound waves produced by the voice are barred from spreading by consecutive reflections from the wider end of the megaphone tube. This causes the loud sound of the voice of the person reaching larger distances. A bulb horn also works on the similar principle of reflection of sound, just like the megaphone. Soundboard. A soundboard is a curved-shaped board that is placed at the back of the speaker in large halls, rooms, or auditoriums so that the sound reaches to people sitting at the back. In large rooms, halls, and auditoriums, the sound can be absorbed by walls, floor, roof, ceiling, and even clothes of persons sitting inside. Hence, the sound does not reach to larger audience. Using soundboard helps in solving this problem by reflecting sound evenly to all places of the hall. A soundboard works on the principle of multiple reflection of sound. The concave surface of the soundboard reflects the sound of the speaker to the audience and thus avoiding the spreading of the sound in different directions. Range of hearing in humans.
You may be surprised to know how the bats travel at nights in the dark without colliding with any obstacles. They emit sound waves of frequencies more than 20,000 Hertz, which cannot be heard by human beings. They hear the reflected sound from obstacles and navigate in the dark. The sound of frequency more than 20,000 Hertz is called ultrasonic sound or ultrasound. Human ear cannot hear a sound of frequency less than 20 Hertz. It's called infrasonic sound or just infrasound. That is the reason you cannot hear the sound produced by the vibrations of pendulum, but you can hear the buzz produced by a bee, as the frequency of the sound wave produced is in the audible range. The audible range of sound for human beings is from 20 Hertz to 20,000 Hertz. Children under the age of 5 and some animals like dogs can hear up to 25,000 Hertz. As people grow older, their ears become less sensitive to higher frequencies. Sound produced by vibrations of earth before earthquake is infrasound, which cannot be heard by human beings. Ultrasound. Sound waves having frequencies greater than 20,000 Hz are called ultrasonic sounds or ultrasound. The ultrasound is produced by some animals like dolphins, bats, rats. Moths of certain families can hear ultrasound produced by bats, and they can protect themselves from capture by bats. Dogs also can hear ultrasound. The ultrasound has very useful property of traveling along a well-defined path even in presence of obstacles. This makes it very useful tool for industrial applications.
Hearing aid. People with hearing loss may require a hearing aid. A hearing aid operates on a battery. The device consists of microphone which receives sound waves and converts them to electrical signals. These electrical signals are then sent to an amplifier that makes them louder. A speaker of hearing aid receives these amplified electrical signals, which converts them to sound and sends to the ear. Applications of ultrasound. Ultrasonic sound is used to detect internal cracks, flaws, and other defects. Ultrasound is used in industry to clean parts that are hard to reach, like electronic components, machines, and spiral tubes and pipes. The high-frequency ultrasound waves stir up the cleaning solution, thus loosening and detaching foreign particles from the objects. Ultrasound waves are used to investigate human organs for medical and surgical diagnosis. Ultrasound scans are also used to check the development of the fetus inside the mother's womb as well as detect any growth abnormalities. It is found to be safer than the X-rays. Ultrasound is used to break kidney stones into smaller particles to flush them out with urine. Sonar.
Sonar is an acronym for sound navigation and ranging. Sonar measures the distance, direction, and speed of underwater objects using ultrasonic waves. Sonar consists of a transmitter and a detector. It is installed in a ship or a boat. The transmitter produces and transmits ultrasonic sound waves. These waves travel through water. They get reflected back after striking the object on the seabed. The reflected waves are sensed by the detector. The detector converts the ultrasonic waves into electrical signals which are appropriately interpreted. The time interval between transmission and reception of the ultrasound is recorded. If the speed of sound in seawater is equal to v and time interval is equal to t, then the total distance traveled by ultrasound 2d is equal to speed into time. Therefore, 2d is equal to v into t. Hence, the depth of the seabed d can be determined. Uses. Sonar technique is used to measure the depth of a seabed. It is used to locate underwater hills, valleys, submarines, icebergs, and sunken ships.
Let us now solve numerical examples based on concept of echo. 1. A submarine emits a sonar pulse, which returns from an underwater cliff in 1.02 seconds. If the speed of sound in salt water is 1,531 meters per second, how far away is the cliff? Solution. Let us first write the given data. Time taken by sonar pulse to return, t, is equal to 1.02 seconds. Speed of sound in salt water, v, is equal to 1,531 meters per second. To find the distance of the cliff from submarine, d, distance travelled by the sonar pulse is equal to 2d, where d is the distance of the cliff from submarine. Distance d is given by v into t divided by 2. Substituting the given values, we get d is given by 1,531 into 1.02 divided by 2. d is equal to 780.81. Thus, the distance of the cliff from the submarine is 780.81 meters. Structure of human ear.
Human beings hear sound through one of its most important organs, the ear. It converts audible pressure variations in air into electrical signals. These signals travel to the brain via the auditory nerve. There are three major parts of the ear. 1. External ear. 2. Middle ear. 3. Inner ear. The external part is called the pinna. The pinna collects the sound and is carried by auditory canal to the eardrum. The eardrum is a thin tympanic membrane. It is set into vibrations due to the pressure variations in the sound reaching it. When a compression of a medium reaches the eardrum, the pressure moves it inward. When a rarefaction reaches it, the eardrum moves outwards. The vibrations of the eardrum are amplified and carried to the inner part of the ear. The auditory nerve connects the part of inner ear to the brain. There is a snail-like shell in the inner ear called cochlea. Cochlea is responsible for recognizing the qualities of sound, that is, loudness and pitch. In cochlea, the vibrations received by the eardrum are converted into nerve impulses or electrical signals. These signals are sent to the brain via the auditory nerve. The amplitude of vibration of membrane gives the brain a measure of loudness of sound.